Swayam Prabha. Digital India. Educated India.
Hello everyone. In this class we will discuss prime field and prime subfields of a field, and talk about extension fields and so on. So, first of all, what is a prime field? Prime field is a field which does not have any subfield. For example, we have considered the field 0 1 where addition is modulo 2 and multiplication is natural. So, this is the field of two elements, this is a prime field. In general, you take any ZP where P is a prime number, we have 0 1 2 up to P minus 1. Right. Under modulo P addition and multiplication, this is a prime field, these are prime fields. Now, similarly, the field of rational numbers is a prime field. Okay. So, you can check that there is no subfield simply because if you take any subfield should have 0, it should have 1, and then once 1 is there, 1 plus 1 should be there. So, 2 is there, similarly 2 plus 1 3 is there. So, all positive integers are there, and then if 1 is there, its additive inverse minus 1 is there, similarly minus 2 is there. So, all the integers are there. Now, once all the integers are there, inverse of all non-zero elements should be there because Q is the field. So, because we are talking about a subfield. So, 1 by 2, 1 by 3 and so on are there, and then once you multiply 1 by 3 with 2, you get 2 by 3. So, all rational numbers positive and negative are there, which just makes the whole field of rational numbers Q. So, there is no proper subfield of Q, and hence this is also a prime field. Now, for any field, like for example, let us take the field of real numbers. For any field, there is a unique smallest subfield, and that is called the prime subfield. Okay, its prime subfield is Q. Why? Because take any subfield K, that subfield must have, by the same argument as before here, it must have all the rational numbers in it. So, Q must be in K. Okay. And so, K is a subfield, then by this same argument Q is a subfield of Q is a subset of K, and Q itself is a subfield. So, Q is the smallest subfield of R. So, Q is called the prime subfield of R. Now, similarly, we have also considered extension fields of the binary field. For example, we have talked about F4 where it has 0, 1, x and 1 plus x under multiplication modulo x square plus x plus 1, and addition is binary coefficient wise. So, this is a field and its prime subfield is the binary field 0 1. This is the prime subfield. Now, we have discussed two types of prime subfields so far. One is Q, the rational numbers, the other is like 0 1 or even ZP type of fields in general. For p equal to 2, it is F2. And in fact, next result says that these are the only prime subfields. For every field, either the prime subfield is of the form ZP or it is Q. So, to be more specific, take any field F, if its characteristic is 0, that is, however many times you add 1 with itself, you never get 0, okay, then the characteristic is called 0 in that case. If that happens, then the prime subfield of this field is Q. Again, by the same argument as before, you can show that all the rational numbers belong to that field, and so that and they form a subfield. Now, if the characteristic is non-zero, then we know that it is a prime number. It is P prime, then its prime subfield is ZP. Basically, we are talking about Q and ZP, but to be more precise, what we should say is that its prime subfield is a field isomorphic to Q, and in this case it is a field isomorphic to ZP. Okay. So, now we will talk about algebraic elements and algebraic extensions of a subfield of a field. So, what is an algebraic element? Suppose we have an extension field F of a field K. Okay. These are fields, and you take any element theta in the extension field. We say that theta is algebraic over K, over the subfield, if there exists a polynomial f(x) over K such that theta is a 0 of that polynomial, that is f of theta is 0. Okay. The term algebra often refers to polynomials. So, there exists a polynomial over K of which that element is a 0. This is not always the case for all kinds of elements in field extensions. For example, if you take real numbers, it is an extension field of Q, and if you take a transcendental number like E, there is no polynomial over rational numbers with rational coefficients whose for which E is a 0. Okay. Now, if the extension field, all the elements are algebraic in an extension field, then you call this an algebraic extension. Algebraic extension of K if all elements in F are algebraic over K. So, algebraic extension means this: all elements in the extension field is algebraic over the subfield. Now, if we take a field and an extension field again, so we are explaining some, we are introducing some new nomenclature and new terminology language now. So, if we take any subset of elements from F, okay, we can extend the field K. So, we have this big field F and there is a small extension, a small subfield K. We can put some extra elements and take a bigger field which includes those extra elements. So, if we take a subset M of F, then we are asking what is the smallest subfield of F that contains K as well as M. So, that is an extension field of K which has all the elements of M and that is the smallest such extension field. So, that is denoted by K of M. Okay. This is the smallest. To be more specific, this is the intersection of all subfields of F containing K union M. All the elements of K is a subfield of that and all the elements of M are also there in that field. So, that is the smallest subfield obtained by adjoining the elements. We say that that is the subfield obtained by adjoining the elements of M with K. So, if you want to put the elements of M and construct a bigger field, you have to include some more elements because it has to satisfy the conditions of a field, and that is the field we will get. That field we will get is called K of M, the field obtained by adjoining the elements. If M is a finite set, it has elements like theta 1, theta 2 up to theta n, then we simply denote this by K of theta 1, theta 2, theta n, and if it has only one element, a singleton like this, we simply denote it by K of theta. Okay. So far we have talked about characteristic the prime subfield of a field. Either it is rationals. If the characteristic is 0, it is the field of rationals. If the characteristic is a prime number p, then it is ZP. We have talked about algebraic elements and algebraic extension of a subfield, and then we have talked about adjoining some elements with a subfield to obtain a bigger field, which is denoted by K of M. Now, K theta, if we adjoin one element, the extension field we get is called a simple extension. Okay. Now, we will discuss minimal polynomial of an algebraic element, minimal polynomial. So, again consider an extension field f of k, and theta is an element of f which is algebraic. Consider set of all polynomials over k, the subfield, set of all polynomials over k, that is in k x, such that f of theta is 0. This is an ideal. This is an ideal of k x. This you can check easily, because if addition minus f, additive inverse minus f is also in this, if f is there. Now, f theta is 0, minus f of theta is 0. If f theta plus f theta is 0, g theta is 0, then f plus g of theta is also 0. F times g of theta is also 0, because that is simply f theta times g theta, and so on. So, not only that, you can multiply f by any polynomial g, and that is also 0. So, it is an ideal of k x. Now, we know that k x is a principal ideal domain, which means that any ideal is a principal ideal, that is, it is generated by a single element. and in particular for ideals of kx and similarly also for integers, the ring of integers, we know that every ideal, it is easy to find a special type of generator element, which is in the case of kx the smallest degree monic polynomial in that ideal, that will always generate the ideal. In fact, that is the way we have also proved that it is a principal ideal domain. So, that particular element, that is, we take the smallest degree monic polynomial. Monic means the leading coefficient is 1. This is called the this is defined as the minimal polynomial of theta. Let us call it G, okay. G, which is the smallest degree monic polynomial in this ideal, and hence it. So, we know that G generates this ideal. G generates this ideal, and because it generates the ideal, it is clear now that for any polynomial f(x), f theta is 0 if and only if G divides f. Okay, f theta is 0 if and only if G divides f. So, in other words, what you are saying is that if you are given any polynomial and we want to know if theta is a 0 of that polynomial or not, we simply need to check whether it is a multiple of the minimal polynomial. All polynomials which are multiples of the minimal polynomial, they have theta as 0 and no other polynomial. Now, the other interesting thing about the minimal polynomial is that G is irreducible. This is, let us call it a lemma, G is irreducible. Why is that? This is simple, because if G had two non-trivial factors, let us say G equal to h times phi, two polynomials. Okay. If this, then G theta equal to 0 implies h theta times phi theta is 0, which means either h theta is 0 or phi theta is 0. So, but G is the smallest degree monic polynomial. So, h and phi cannot have a smaller degree polynomial other than 0 itself, or 1 itself. Okay, because of course, the factorization can be simply 1 times G itself, which is a trivial factorization. So, this means that degree of h cannot be strictly less than degree of G. Okay. So, it is a contradiction. This kind of factoring, non-trivial factoring cannot happen, that is h not equal to 1, not equal to phi, this cannot be true. So, G must be irreducible. Okay. So, we have talked about minimal polynomial of an algebraic element in an extension field. We have defined it as the smallest degree monic polynomial in the ideal of polynomials of which theta is a 0, right, and we know that polynomial generates that ideal. So, we immediately have that any polynomial has theta as a 0 if and only if g is its factor. Then we have also seen that the minimal polynomial g is irreducible. Now, if we have an extension field f of k, then f and f, then note that f is also a vector space over k. F is a vector space of k. Suppose this is a finite dimensional vector space. Okay, this suppose dimension of f over k is finite. Then we define f colon k to be the dimension, this dimension of f over k, and this is called the degree of the extension, degree of f over k. So, f colon k is the degree of the extension f over k. Now, if this is a finite extension, then immediately we can prove an interesting result, which says that if f is a finite extension, which means that this dimension is finite, this quantity is finite, it is a finite extension of k, then it is algebraic. Over k. Why is that? Because if you take any element, so what you need to prove is that every element is algebraic in F. So, let us take any theta in F. So, so we know that it is a finite extension, which means that it is a finite dimensional vector space over k. So, let us take these elements 1, theta, theta square, theta cube, this infinite sequence of powers of theta. Now, these cannot be linearly independent, because this is a finite dimension, this cannot be linearly, these are linearly dependent over k, because f is a finite dimensional vector space over k, it cannot have an infinite number of linearly independent vectors. And if it is a linearly dependent set of elements, then of course, that means that there is some finite number of them which are linearly dependent. Let us call it I equal to 0, I equal to 0 to n a I theta power I, where theta power 0 is assumed to be 1. Okay, we know that it is 1. So, this is equal to 0 for some a1, a0, a1 up to an, some scalars in k. Okay. So, these are linearly dependent, the powers of theta are linearly dependent, which means there is such a linear dependence relation, and that immediately means that theta is a 0 of the polynomial, theta is a 0 of the polynomial f x, which is I equal to 0 to n a I x power I, because if you put theta in place of x, you get exactly this quantity, which is 0, right. So, this is equal to f theta. So, that proves that theta is algebraic. Over k. Now, every finite extension is an algebraic extension. This is what we have shown. Now, this quantity has a chain rule relation. So, this degree, if you take f is an extension field of L, which is an extension field of K. If you take a chain of extensions like this, then this lemma says that the degree of f over K is the degree of f over L times degree of L over K. Okay. So, the proof is quite routine. So, you want to prove that the dimension of f over K is given by the dimension of f over L times dimension of L over K. So, we want to, so we have these quantities. So, what it means is that f has a basis, let us call these numbers m, small l, and this let us call it n, okay, this quantity. So, we want to show that n equal to m times L. So, f has a basis with m elements in it. So, let us call it alpha 1, alpha 2 up to alpha m over L, and L has a basis of, let us say, beta 1, beta 2 to beta small l over K. Then what we need to construct a basis of f over K having m times L number of elements, right. So, then that would prove that the dimension of f over K is indeed m times L. So, n equal to m times L. So, what will be the basis of f over K? So, one obvious candidate is take all multiples of alphas and betas. So, there are m alphas and L betas. So, you will get m times L alpha betas. So, in other words, you take alpha I, beta j, where I lies between 1 to m and j lies between 1 to L. So, this forms a basis, this is a basis of f over K. How do we prove that this is the basis of K? Just use dimension. One can show that this is a linearly independent set and it generates all the elements, and this is quite routine proof. So, I will skip this part of the proof. This is left as a homework, which is simple. So, this is a nice chain rule which is quite intuitive. It says that if you extend a field 2 times, first time you extend there is a dimension, that your degree of extension, second time you extend that field again, another degree of extension or dimension of that over that field. So, the overall extension from the smallest to the largest, that degree of extension is the product of the degree of extensions in each step, okay. And this is quite simple and intuitive to remember. So, just to do a quick recall, what we have done is we have first defined prime subfield, and we have seen there are only 2 types of prime subfields for any field. For characteristic 0 it is Q, for characteristic prime characteristic it is ZP. Then we have seen what is an algebraic element and what is an algebraic extension of a field. Then we have talked about simple extension and adjoining any set of elements with a subfield, and then we talked about minimal polynomials and minimal polynomial of an algebraic element and its simple properties, like the minimal polynomial is irreducible and all other polynomials with theta as a 0 are obtained by multiplying that minimal polynomial with some other polynomial. And then we talked about the degree of an extension. We have shown that every finite extension field is an algebraic extension. Then we have proved this simple chain rule kind of result for the degree of extension. Okay, we will now discuss some results about simple extensions, that is extension field obtained by adjoining one element to a field, and then we will discuss what is known as splitting field. So, the first result is about a simple extension. Suppose we have theta, an element of an extension field, and it is algebraic of degree n over the field k. So, f is an extension field of k, theta is an element of the extension field which is of algebraic of degree n over k, and suppose the minimal polynomial of theta is g, minimal polynomial over k is g, and it is of degree n. Then the following results hold: k theta is isomorphic to k x by g. K theta is the simple extension that is obtained by adjoining theta to k. Then the degree of k theta, the dimension of k theta over k is n, and the elements 1 theta, theta square up to theta power n minus 1 forms a basis of k theta over k. The third is that every element in k theta is algebraic and the dimension of k alpha, algebraic of, simply we can say algebraic of degree dividing n, degree of alpha divides n, that is its minimal polynomial has a degree which divides n. So, let us discuss the proof outline of these results. So, first result says that k theta is isomorphic to k x by g. We will define a ring homomorphism and show that it is isomorphism. So, let us define first of all a map, let us call it pi, from k x to k theta, where every polynomial goes to its evaluation at theta. Clearly, f theta belongs to k theta. So, it is clear that this is a ring homomorphism. And its kernel is given by set of all polynomials in k x which has theta as a 0, that is f theta is equal to 0. and we know that this is an ideal and it is generated by the minimal polynomial of theta, which is g. So, by ring homomorphism theorem, what we know is that k x by this kernel, which is generated by G, this is isomorphic to the image of pi, which is a sub which is in k theta. Now, we also know that k x by G is a field. This is a field. So, image of pi is a subfield. Of k theta. Now, we can also see that k is a subfield of k this image, because every element A in K goes to A itself according to this map. So, it is there, A is there in k theta, in the image. So, K is a subfield. So, what we have is that K is a subfield of image of pi, which is a subfield of k theta, and we also know that theta belongs to image of pi. Why? Because x goes to theta, x goes to theta, pi of x is theta, hence theta belongs to the image. Now, k theta is the smallest field that contains theta and k both, and now we see that k is a subfield of image of pi and theta is also there in image of pi, hence image of pi must be equal to k theta. So, image of pi equal to k theta. So, what we see is that this is isomorphic to k theta itself, and that is what we wanted to prove. Now, the next result says k theta, the dimension of k theta is k and its basis is this set, and we will simply show that this is a basis of k theta over k. So, the proof of this is that we will show that 1 theta theta square up to theta power n minus 1 is a basis of k theta over k. So, how do we prove that? We prove by proving that it generates all the elements of k theta and they are linearly independent. So, first of all, we note that every element in k theta, by the previous proof, every element in k theta is of the form f of theta, where f is a polynomial. So, every alpha in k theta can be written as alpha equal to f of theta for some f in k x, a polynomial. Now, any polynomial f like that can be divided by g, and we can get a quotient and a remainder r, so that degree of r is less than degree of g, which is n, or r equal to 0. So, we can take that polynomial r itself, and we can see that alpha equal to f theta equal to q theta g theta plus r theta, and g theta is equal to 0, because g is the minimal polynomial of theta, and so this is equal to r theta itself. So, alpha can be written as a polynomial evaluation of theta where the polynomial is of degree less than n, strictly less than n, and that means it is a linear combination of theta 1 theta theta square up to theta power n minus 1, because R is a polynomial of degree less than n. So, we see that any element in k theta like this can be generated as a linear combination of these elements. Now, we will show that these are linearly independent. So, if you take any linear combination, let us say a I theta power I equal to 0 to n minus 1, if this is 0, then we will show that all the ai's must be 0. How? Because then we can write a of theta equal to 0, where a x is defined to be a polynomial which is with a i's as the coefficients, a naught plus a 1 x plus up to a n minus 1 x power n minus 1. So, now because a theta is equal to 0, we can see that this must mean that a x itself is 0, because a x is a polynomial of degree less than n. Degree of a is less than n, which is the degree of its minimal polynomial of theta, right. So, a x is a smaller degree polynomial than the minimal polynomial which has theta as a root, and that cannot be true. So, the only possibility is that a x itself is 0. Okay. So, which means this all the a i's, a naught equal to a 1 equal to a 2, all the a i's n minus 1 equal to 0. So, that proves the second part. It proves that these elements are a basis. Now, the third part says that every alpha is algebraic of degree n, degree which divides n. So, to first show that every element in k theta is algebraic, it is simply sufficient to observe that k theta is a simple it is a finite extension, because these are a basis 1 theta theta square up to theta power n minus 1, this forms a basis, and so it is a finite dimensional extension. This is a finite dimensional extension, and hence it is algebraic extension, is algebraic. That means every element in k theta is algebraic. Then any element alpha in k theta is algebraic. And now to show that its degree divides n, the degree of alpha divides n, we simply note that the dimension of k theta over k can be written as k theta k alpha times k alpha k, and hence, and this is equal to n, this is the n dimensional extension k theta is, and hence k alpha k, this is the degree of alpha, this divides n. This proves the third result. Okay. Now, the next result we consider any polynomial f in k x, and which is irreducible. We take any polynomial that is irreducible, over k, and the result is that there exists a simple algebraic extension that is a simple extension obtained by adjoining a root of f with a root of f as the defining element. Okay. So, what we are saying is that we can there is a simple algebraic extension of k that can be defined where a root of f will be there, and that will be the defining element of that extension field. So, the proof is by construction. So, we simply take the field extension kx by f. Now, any polynomial in kx, let us say any hx, there is a corresponding element in the quotient kx by f, which is denoted by hx in square bracket, is basically hx plus the ideal f, ideal generated by f. So, every polynomial has its coset of the ideal, and that is the element, corresponding element in the quotient ring. Now, we know that this is also a field. This is a field because f is irreducible. So, this is an extension field, this is an extension field of k. Why is it an extension field of k? Because there is an isomorphic copy of k inside this, because for every a in k, every scalar a in k, there is a corresponding element mod a, and this is an isomorphism. One can check that this is an isomorphism. So, this is a one-to-one mapping. So, this gives a copy of k inside kx by mod f, and hence this is an extension field of k. Now, this field has a root of f as a defining element. Why is that? Because first of all, note that f of the element x in square bracket, that is the coset of x, that is same as this of f x, which is 0, the coset of 0, that is the ideal itself. This is the ideal itself. So, this element is a root of f x, and this element is there in k x by mod f. So, in this extension field there is a root of f x. In k there was no root of f x because f was an irreducible polynomial, but in the extension field there is a root. Now, one can see that this is in fact the smallest field that contains k as well as this root. Why is that? Because if this element is there, all its polynomial evaluations, let us say h of mod x this must also be there in any field that contains this element. Any polynomial evaluated at that element should also be there in the extension field. So, now on the other hand, these are all the elements in this field, because this is same as this, and so all the elements here are of this form, okay, and all those elements can be also written this way. So, they are polynomial evaluated at this point, which also must be there in that field. So, you see that this has this is the field obtained by adjoining this element to K. So, this result is very significant in the sense that this guarantees that for any irreducible polynomial there is a bigger extension field where it has a root, and in fact that extension field is the smallest field that contains that root and the field K. So, the field can be extended just sufficiently so that it contains a root of the irreducible polynomial. Now, next theorem says that in some sense it doesn't matter which root of an irreducible polynomial we take, the extension field we get, they are all isomorphic to each other. In fact, if you take alpha, beta, roots, these are roots of f x, then k alpha and k beta are isomorphic with an isomorphism that takes alpha to beta. So, you take any two roots of f x, the simple extensions obtained by adjoining those two elements separately, they are isomorphic to each other, and there is an isomorphism which takes that alpha to beta. The proof is very simple. We have shown already that k alpha is isomorphic to k x by f, and we have also shown that this is also isomorphic to k beta, and we know that these isomorphisms can be defined in such a way that the element x here goes to beta, and there is an isomorphism this way also which goes to alpha. And hence, you take the inverse isomorphism this way. So, suppose this is a mapping, this is pi and this is let us say sigma, then we take pi sigma inverse, that gives an isomorphism which takes alpha to beta. Okay, the next thing is, for any polynomial we want to now claim that there is an extension field where you can split the polynomial, which means that it is all the roots. If the polynomial is of degree n, then it has n roots in that extension field. a polynomial can be irreducible, it can have many irreducible factors, no matter what, you can get an extension field where all the roots of that polynomial, exactly the degree, so many number equal to the degree, so many roots will be there in some extension field, counting multiplicities. So, first of all, first a definition, splitting field. So, if you take any polynomial f over k and f is an extension field of k, then f splits, we say that f splits over f if f can be factored linearly. Okay. So, it has linear factors, that means we have found n roots of f in that field. So, the polynomial is over k, but there is an extension field f where we say that f splits if f has n roots, or n can be f can be written in this way, factorized into n linear polynomials. Now, not only that, if f is the smallest such field, which means that it is the intersection of all such fields, then we say that f is the splitting field of that polynomial. F is the so, in other words, if f is equal to k extended by adjoining alpha 1, alpha 2 up to alpha n, then we say that f is the splitting field of f. Now, the next result, which summarizes a very important fact about splitting fields, is that for any polynomial f, a splitting field exists, okay, and it is unique up to isomorphism. So, every polynomial f in Kx has a splitting field and any two splitting fields are isomorphic under an isomorphism, a map that maps, that first of all fixes elements of k, the base field k, and maps the roots of f to each other. So, what we are saying is that every polynomial has a splitting field and it is unique up to isomorphism, that is any two splitting fields are isomorphic to each other, and not only that, you can define an isomorphism that fixes all the elements of k, that means they are not changed, okay, they remain unchanged under that mapping, and they map the roots of f to roots of f. Now, this detailed proof of this we will not go into, but basically the proof can be done by first of all factorizing f into irreducible polynomials and then taking the splitting field of each irreducible polynomial one by one and extending it more and more, finally getting the splitting field of the whole polynomial. So, for example, we know that over the real field, you take any polynomial, quadratic polynomial like 2x square minus 1, 2x square plus 1, or any polynomial, the splitting field, if it is not irreducible, then this itself is the splitting field. If it is irreducible, any quadratic polynomial, if it is irreducible, then you can extend this to C, where its roots will be there, and it is the in fact splitting field for any polynomial. In fact, this is very special field where all polynomials over R splits, and in that sense this is what is known as the algebraic closure of R. You do not need any further extension of C, because there all the polynomials have all the roots possible, that is, if degree n polynomial has n roots. We will see that for finite fields that is not so simple. You take any polynomial, you can extend the field so that you get the splitting field, but then you can take another polynomial and you have to extend again and so on. So, okay, that is all for now. Thank you.